maybe you thought that you could handle the same problem with multi-threading, also multi-threading the cores. Have you considered?
Potentially.
Of course, you won't have the locality between the streams, perhaps, if there's locality.
Yeah, so your argument is that, if I can restate it, is that yes, you may be in an inefficient scenario where a thread is stalled, but since you're doing multi-threading, the core may still be busy with another thread.
That's right.
There could be some truth to that. Eventually it runs out of gas, though. If you have too many threads stalled, then you're going to suffer from inefficiency. So I think the argument still holds also in a multi-threaded case, but perhaps you're right that it's a little less important in a multi-threaded. I should point out that the 32-core device is a 32-threaded device, so it's not that different from a multi-threaded.
So the core itself is?
The core itself, no, each core is single thread, but the SoC as a whole is a 32-thread device. So it's not all that different from a multi-core device with multiple threads in each core. Yeah?
Just a basic question. Why is your iCache 37-way associated?
Because 38 didn't fit.
I mean, is there something intrinsic about these workloads where you have a lot of conflict misses? Or?
Yeah, we did actually do some benchmarking and found that for some Linux applications we needed more than 32 kilobytes. Otherwise our miss rate would go up. But we couldn't afford 64 kilobytes. So we squeezed in as much as we could. Is the real answer. But I was also correct in saying that because 38 didn't fit. Yeah.
So I would be curious to ask whether the mesh interconnect was ever a consideration, or you wanted to go with the multi-socket design from the very beginning, with the crossbar.
Mesh interconnect on chip, you mean?
Yeah.
No.
It was never a consideration.
No. Not in our device. Eventually, you'll have to put some hierarchy, I don't know if hierarchy is the right term, but some partitioning maybe is a better term. But we really want to keep a very simple software model of our device until we have to do something else.
Mm-hmm.
So we will be drug kicking and screaming into a system where the memory latencies and the cores are variable latency from each other. However, I would be surprised if we get there eventually.
Mm-hmm. Yeah, that's sort of required if you want to scale up.
If you're talking 1,000 cores,
yeah,
you'd have to, right. But we're not 1,000 cores yet. So where exactly in the middle that happens, I don't know.
Mm-hmm.
But for 32, 48, we think we're fine. And I think I'm very confident that up to like 64, it'll be an excellent solution. When you get up to 128, well, then it might get a little more interesting.
So right now you have hardware benchmark results that actually support your statement that you have no asymmetries in memory controller access between different cores.
That's right. There's literally in this device no asymmetries.
Okay.
Any other questions? Yeah.
For measuring power, like estimating power, you track some counters.
Yeah.
Couldn't you do something simpler, probably track how much current it is drawing or something? I was curious.
How much current is, I forgot to mention that all this, that I show on this slide, it's digital logic. So to measure the amount of current, you would require some sort of analog logic or something. What we came up with is technique via digital logic to do this. I should have mentioned that, and I'm glad you asked that question. So all that we're looking here, the events and everything are all digital.
And this logic is replicated at a per core level or
Yes.
something? Okay.
It's replicated on every core. That's right.
So your claim is basically this is less area than like a shut resistor plus an ADC sort of thing.
It's less area, that is true. It's also analog logic is a little more messy to validate and verify than digital. Here, this is all quite simple. Okay, so any of you who need to jump out are free to. So I think we're done with the more general formal presentation and are moving on to discussion on potentially Cavium may supply evaluation boards, including this 68XX that I discussed. So let's go through that. So here's what the board looks like. Some important things. If I can get my pointer to work here. Right now. So right in the center there, you can see actually buried under a fan is the 68XX device, and right near it, on each side, are 4 DDR3 slots on this board. So that's an important aspect of this design. Another important aspect is the bottom and lower right, that you see those things called QLMs. So what QLMs are the SerDes that are coming off the chip, and they're a way to hook up the chip to the external world, for example, an Ethernet port or a 10 gig Ethernet port or whatever. So there's also things like USBs and UARTs, and there's a management Ethernet port. All are also, but that's really most of what this motherboard is here. So it's powered by standard ATX power supply. I mentioned those 5 QLM connectors for I/O modules, and on the next slide I'll show you some example I/O modules. 8 DIMMs, we talked about that. We have UARTs, serial ports. We have USB ports, an Ethernet management port, which I think is 10100. BJTAG is actually a way to debug, go very low level debug of the MIPS cores. And there's also compact flash storage, so that would tend to be how you add your boot software beyond the flash devices. So the I/Os that you can connect to this device, here's some examples. So for example, on the top, on the left here, is a connector that connects a QLM connector, which is on the top, to 4 gigabit Ethernet RJ45s on the bottom. So you can plug that into the main motherboard, and then you've got gigabit Ethernet connectivity, standard RJ45. So the middle one there is similar thing. It's the QLM connector on the top, and on the bottom, I think that's either an SFP or an SFP plus. I don't know for sure. That it gives you a 10 gig Ethernet connection. And on the right is a little bit differently oriented. The QLM connector is on the left, and so that that connector actually allows you to have the 68XX be a PCI Express device, because that's a PCI endpoint card. So the combinations of the motherboard that I showed you 2 slides ago and this these QLM modules will be what you would get. Yeah.
Is QLM something you would see in like an end unit? You know, if you're going to put one of your chips into a router, for example, is that sort of a common thing, or is this just for sort of the debug exploration phase?
For us, it's a common thing. For us, QLM stands for quad lane module. It's basically 4 SerDes lanes. A unit that's 4 SerDes lanes. QLM, I think, is just our term.
Okay.
But it is what the actual IOs of our chip are. SerDes IOs, I should say. So we are embarking on a program to, and we've targeted a number of esteemed universities, such as your own, for 68XX boards. Our plan, we'd like to work with you and give you boards so the students can do projects, so that researchers can do research projects. Jim Ballingle is a better, he's in charge of this, and he would know more, but the plan is to have for those that want to become very adept at Octeon, there'll be a workshop in Boston in May. There we're hoping to have presentations of Octeon-based projects. We also are having a global multi-core channel. It's a programming contest. It's open to all undergraduates, or I think graduates as well. And there'll be details of that coming out in March. So resources for this program, we have a university program website that's listed there. Important thing that if you're interested in this is Jim would like you to sign up for the Cavium Users Group website, cnusers.org. There's a Facebook page, and we have specific contact people in the company. Jim Ballingle, the first one, and others as well. So our hope is to provide you with some real Octeon hardware to do interesting projects on. And here's some, I don't know, crazy ideas for what kind of projects you could do with Octeon. Octeon's well suited for networking, so for us it's natural to say something like bumping the wire. And what do we mean by that is that packets flow in, go through our chip, are processed, and flow out. You can use your creativity to figure out what more specifically you'd like to do, but examples here: monitor in-packet flows, use the accelerators that I mentioned to do packet inspection, perhaps develop a intrusion detection algorithm. Another crazy idea we have is performance trade-offs and management to optimize the performance of the cores, vary the number of cores, vary the workloads, change things from software to hardware, figure out what the different power profiles of that are. And another final one is their optimized parallel program code for specific workloads. So if you have a specific workload that, say, runs on Linux, it might not be very difficult to port that to an Octeon device, since we can run Linux also. And run compilers and all the stuff that all the programming tools that you need. So that's all I have on the project. If there are any questions, I'm happy to answer.
I have a question.
Yes, sir.
How much programmability / configurability does your hardware schedule have? Is it something that is it ridiculous to dream about user space configurability of that, or?
It's not ridiculous, but to do user space, you are going to have to open up some things to the user. In fact, we commonly do tricks like that.
Mm-hmm.
I mentioned Linux all the time in my discussion, just because it's something you understand. We also have something that we call either bare metal or simple executive, which is basically a way that where there's no Linux, and you're writing an application in C that's writing straight on top of the hardware. So you could certainly write a user-level app in bare metal / simple executive that has access to everything.
Mm-hmm.
Another interesting possibility that we have is, now for years now, we've supported the ability to have this simple executive style, but it's actually a process inside a Linux kernel. So it runs a little slower when it's inside the Linux kernel, but not too bad. But you get some of the benefits of Linux while still having a lot of the access of the bare metal / simple executive application. So I would say the answer is yes to that, and we have a variety of tools, but it's not just a simple yes without explanation.
And you provide the SDK with the board, right?
Yes.
Okay.
Any questions? Well, if not, I thank you for your attention. I enjoyed visiting you and presenting this to you.
Thank you.